morning, everybody. My name is Aungst. I'm an engineer at AUC Engineering. The presentation this morning is talking about some of the work that we did on our most recent NSRP project. This was a CAD-to-FEA project. We did this with Ingalls, SSI, and ourselves. And the goal of this was to improve the interface between ship design and FEA analysis. So try to find ways to kind of automate some of the repetitive tasks that are involved in creating finite element models, especially when a lot of analysis has to be done. So I'll give a quick introduction of who AUC Engineering is, and we'll go into what the overall problem that we're trying to solve, what solution we came up with, and then a quick example of what you kind of get out of our solution. So AUC Engineering is an engineering services business with a focus on structural analysis and design. We do work over a variety of industries, mostly aerospace and defense. We do things like dynamics and stress analysis, and fatigue, acoustics, and CFD, and pretty much anything that goes into a structural analysis. Really, over all of that stuff, we spend a lot of time on software development and software tool development, trying to make ourselves more efficient, and also to help customers that we work with become more efficient in structural analysis as well. This really made us hopefully a really good partner for this NSRP project. So the bottom line of what we were trying to solve with this project is we were trying to reduce the time and effort needed to create finite element models of, in this case, shipboard foundations. So there's a lot of information that's already in ShipConstructor. It's very relevant to finite element analysis. So we're trying to bridge the gap between this so that work didn't have to be replicated, basically between the designer and between the analyst in creating these finite element models. In this case, we were working with Ingalls and their finite element tool choice is FEMAP. So this solution is specific to FEMAP. We did our best to kind of make the whole process of what we made fairly modularized. So we separated the part that interacted with ShipConstructor with the part that interacted with FEMAP. So if someone came later and wanted to do this with HyperMesh or an X or some other tool, it would be a relatively low effort to do that. So the general workflow, kind of the as-is process of how you build finite element models isn't really specific to shipbuilding. It's really across all industries, and this is exactly the same sort of process I go through every day in my analysis. Really, the process of making finite element models isn't necessarily difficult. It's just very time-consuming. It's very manual. So our goal here was to try to automate some of these things. So the typical workflow is you would get some sort of geometry, some sort of CAD out of ShipConstructor from your designer, and then you would import that into your tool of choice. But what you've lost here is you've lost all your metadata. So you get just the geometry into your FEA tool. And then from there, you need to go back to ShipConstructor and go grab all the things like your materials, all your properties. These are all things that you have to make by hand in your FEA tool. And these things are things that depending on how many different thicknesses, depending on how many materials you have, become manually intensive and they're kind of prone to errors. Oftentimes you've created your model, you have to go back and forth between whatever your CAD tool is, whatever your finite element tool is, to try to make sure that what you built a model of is actually what was in the CAD tool. Also, in the case of these foundation analyses, obviously the foundation is supporting some sort of equipment, so you have to go in and figure out what the CG of that equipment is that you were continue to analyze, make sure that you have the CG correct, make sure you have the maximum, manually create all those things in your finite element tool. So basically, the new workflow that we proposed for this project is basically all the things that in the last slide were manual things. Creating the geometry, idealizing the geometry, creating the physical properties, creating the material properties. We've essentially created an automated code that does all this for you. So it takes all of what are the 3D geometry in ShipConstructor and creates an idealized 2D version of it, basically that's ready to mesh. And all the different physical properties, all the different material properties that you need for that, we've created them automatically within FEMAP and then assigned them to the geometry in FEMAP. So all that's left in the process is to go and basically create a mesh on that surface, and it already knows what thickness and what material it's supposed to be. And then in addition, for any equipment or spools or systems that are in the model, we automatically go and create lump mass elements at those locations. Basically, based on the CG and the mass that are reported in ShipConstructor. So kind of the technical details of what we come up with, it's basically a three-part solution. So the first part of this is obviously ShipConstructor. So to figure out essentially what you want to analyze, you create an alternate product hierarchy. These contain all the parts that you're intending to analyze. And then from there, you use EnterprisePlatform to export that information into an XML file. And this XML file has basically the unique identifiers for all the parts that are included in that assembly. And then from there, it gets passed on to the first part of this, which is called ShipPDX. So this is Ship Product Data Exchange. And what this does is it reads those XML files, it gets those unique identifiers for all those parts, and then it queries the ShipConstructor database directly. So it goes in and it finds all the information about the polylines, about all the parts, all the stocks, all the systems, basically querying everything out of the database, and it puts it in what we call these neutral files. This is that tab limited file. It's human readable, it's easy to parse. It basically contains all the information of what you're trying to analyze. And then from there, we pass into the second part of the process, which is called SPX to FEMAP. So what this does is it reads in all those neutral files that we've written out, containing all of your assembly information, and then it uses FEMAP's API to essentially recreate an idealized version of that automatically for you. So I'll go into detail what each one of these pieces do. So the first one I mentioned was ShipPDX. This actually wasn't necessarily an outcome from this particular project. This was work that AT had done previously in SBIR through NAVC back in 2009 and 2012. It originally had a very different purpose. Then the purpose was that NAVC wanted to basically wanted to translate from one CAD package to another. So we were trying to dump all the information out of a ShipConstructor database for the purposes of translating it into another CAD package. It's a very similar problem that you don't want to lose all the metadata that you created in ShipConstructor if you wanted to go try to translate to something else. But in this case, we were able to utilize the same sort of thing, but just for a different purpose. That the same information we wanted to use for that purpose is very helpful for trying to recreate a binary model or an idealized model of whatever you're analyzing. So the kind of the core of what we created this was SPX to FEMAP. So this is a compiled Python executable. It basically runs FEMAP from behind the scenes. So what happens is it opens up FEMAP, it reads in all the files that ShipPDX has export, and it does a whole bunch of API commands. So they're very similar to the same commands that you would have done kind of by hand as an analyst, but these are all things that can be automated and save a bunch of time. And then at the end, it basically saves its current state so the analyst can open it and continue to work from there. The type of output that are created, we can recreate the idealized versions of flat plates, stiffeners, and curved stiffeners, and then obviously concentrated math is very dependent because that was the original intent of this kind of foundation analysis project. And then since then, we're also participating in the LiftShip project, so we've extended this technology to kind of encompass the stuff that we encountered there. So we can now do idealized version of curved plates, and we also do both HVAC and pipe. So the intent here is not to actually do a structural analysis on the HVAC and the pipe. We provide basically geometry curves of what path they take through whatever you're analyzing for the purposes of basically keep-out zones for where you can put temporary bracing for a lift and stuff like that. So I'm going to go through a quick example of kind of what the process is, what you get at the end. This was the model that we used throughout most of the project. This is kind of an excerpt out of the NSRP training model. You can see on the left is what the model looks like within ShipConstructor, and on the right is basically the end result of what you get out of FEMAP. So you can see the pump and the foundation that they were basically the goals of this analysis and all the associated structure that came out behind it. So it's kind of hammering the point home. So the whole goal of this is that what you had in ShipConstructor ends up basically perfectly represented also in FEMAP. So in this case, in the training model, there was like 10 different plate stocks that you can see in the stock catalog on the left. Those are exactly recreated in FEMAP. So they're all automatically associated to their correct material, and the properties are also automatically associated to whatever geometry that we create within FEMAP. And then in terms of any equipment, the names that we've created for the properties obviously match the names of whatever is in ShipConstructor. And then in terms of stiffeners, stiffeners are often multi-parts, so we have an angle or a T or the flange and the web and everything. Those are broken up into separate properties here. You can see this like a ball flat has a separate property both with the G-wedge, flange, and bolt flat. So similarly, this is what you end up with. So this is the different parts of this assembly highlighted, just basically showing that each different type of plate stock has been correctly associated with the geometry that we've created with FEMAP. One part of this project that was kind of relayed to us is that our goal here is to do all of the pre-processing steps of the final element analysis and not necessarily try to do a mesh. So we stopped at basically setting it up all the way up to where the analyst would want to apply the mesh. And then also, since this was a foundation analysis, it's very important. So what we've done here is we go through, obviously, we go look at whatever equipment's called out in the alternate part hierarchy. We go grab where the mass and the CG information is from ShipConstructor, and we make a one mass element at that location so it's ready to attach to the structure. The notes here is what we had been told is that the mass and CG information of equipment isn't necessarily always accurate in ShipConstructor because it's really on the onus of whoever put it in there to make sure it's correct. So basically, in all this stuff, there's a requirement to go through and make sure that what came out, it's going to match it to the ShipConstructor, but there's an intent to try to make sure that it matches up with reality. So as part of this project, we didn't attempt to try to, if we knew two things were connected, we would try to connect them, but we didn't make any assumption that just because things were touching, they were meant to be connected, and maybe we'll revisit that. But so there is a little bit of geometry cleanup that's required on the part of the analyst after it's done. So there's multiple ways that these can be modeled. In this case, you have gussets and stiffeners that lay on top of each other. An analyst may want to mesh them separately and then connect them, or they may want to imprint them and basically just see that they're continuously molded. So this is where we left it. And these are on basically on the analyst to decide how they want to model those things. We do as much geometry cleanup that we were comfortable with, knowing that it was correct. So in this case, oftentimes on these curved edges, there's a lot of control points, a lot of definition points that when they come in as geometry, they kind of get embedded in the curved definitions. So if you go to mesh, these points end up kind of messing up your nice clean mesh. So for these continuous curves, we go through it and make what's called composite curve in FEMAP, basically saying that this is all, basically telling FEMAP all these different line segments are all one part of the curve. And then kind of to conclude, well, this project was intended to do just kind of foundation analysis. Our technology does extend to the full database. So this is what comes out of our code. You can pass in the whole NSRP training database. You can see all the different masses for all the different schools and systems. You can see the lead green is all the pipes, pass, and red is all the HVAC. We haven't tried this to do the curve plates on the outside, but we're going to do that soon. I think that's all I have. So if there are any questions, I'll be happy to answer them.
So is it capable of determining whether or not, or inputting whether or not you want to change the stiffeners from, say, a plate and a flange, or a T versus a beam element?
Yes and no. So currently, based on feedback where we were working with, their process was for all stiffeners, they shell mesh them all. So if there was an angle, they would shell mesh both of them, or if they were T's, they would shell mesh both. The only time that we do any bar definition is for a ball flat. We assume that the web of the ball flat is a shell, and the actual ball is a beam element for a cross section. It would not be difficult to change that. Just no one has told us the geometry
So you were talking about assuming connections. Has any of the weld data associated with potential use of connecting parts? Is that?
We just were Elliot and I were talking about this. So I think early on, at least in this project, I think we were told that all that information isn't always guaranteed to be in there. So it was one of those things that we can certainly rely on. We can do the stitching operations to stitch stuff together, but we were cautious in making sure that we didn't automatically. You're kind of in a quandary. You either decide everything's connected and it's touching, or you decide nothing is connected and it's on the onus of whoever's analyzing it to know that these two pieces are all together.
Absolutely understand that, and I know that there's several of our customers that don't put the weld information in, and if they do, it's specific to a CAD-to-FEA application or a specific to one particular unit that they may want to deal with. I'm just wondering if that might need to eventually be considered. That would actually solidify their connection versus the assumption of the connection. Any other questions?
I got a question for you.
You got a question for
Where
me?
did the ShipConstructor say it's a uniform job? The export to FEMAP, where did the ship?
What the version was what?
What version of ShipConstructor?
Yes.
All of them. It's very, the API for ShipConstructor, at least the things that we use, doesn't change very often. So we just have to make a version that's specific to it. We have to recompile, anytime that there's a new ShipConstructor version, we can recompile a portion that connects to ShipConstructor.
I think the original project was done in 16.
We started in 16 and we're still working our way through getting it implemented at the shipyard. So since that has happened, they have now moved on to new versions. So we are continuously, as new versions of ShipConstructor get released, we recompile for that. So we support them all.
Okay, thank you.
Any other questions? Okay. Thank you, Roger.